Good morning, everyone. I am Desta Tatel, and I am pleased to welcome you all today. We are about to dive into an exciting topic, the application of physics in other fields. Today's presentation is part of our grade 12 Unit 1 curriculum. We will explore how physics concepts are used beyond the classroom, impacting various industries and everyday life. So let's get started and see how physics plays a vital role in different areas around us. Today, we're going to explore medical physics, which is a fascinating branch of physics that applies its principles to medical diagnosing and treatment. Essentially, it helps us understand how physics is used to detect and address abnormal tissues in the body. A pivotal moment in this field's history was the discovery of X-rays by Wilhelm Conrad Röntgen in 1895. This discovery truly revolutionized both science and medicine, opening up new possibilities for non-invasive diagnosis. In fact, Röntgen's work led to the creation of a whole new interdisciplinary branch, medical physics, that combines physics and medicine to improve healthcare. Interestingly, Röntgen himself made the first X-ray photograph late in 1895, capturing an image that marked the beginning of a new era in medical diagnostics. So, as we continue, you'll see how these foundational discoveries paved the way for advanced technologies that save lives today. Medical imaging refers to a variety of technologies that allow us to see inside the human body. These techniques are essential for diagnosing, monitoring, and even treating medical conditions. When we talk about imaging biological samples, there are several different methods used. Some of these techniques rely on electromagnetic waves, like optical imaging, X-rays, MRI, and thermography. Others use acoustic methods, such as ultrasound. There are also chemical and electrical imaging techniques. Among the most common and widely used are MRI, which provides detailed images of soft tissues, X-ray computed tomography, or CT scans, which give cross-sectional views of the body, and high-frequency ultrasound, which is great for real-time imaging, especially in pregnancy and soft tissue examination. All these tools are crucial because they help us visualize the internal structures of the body without invasive procedures. Understanding these different imaging technologies is key to appreciating how modern medicine diagnoses and treats various health conditions. Magnetic resonance involves the absorption or emission of electromagnetic radiation by electrons or atomic nuclei when certain magnetic fields are applied. This principle forms the foundation of MRI technology. Interestingly, the physical principle of magnetic resonance was first described by Felix Bloch and Edward Purcell back in 1946, which was a major breakthrough in physics. Later, Paul Lauterbur and Peter Mansfield developed methods to acquire detailed MR images of the human body, turning this physics concept into a powerful medical imaging tool. So, how does MRI actually work? Well, it all depends on the presence of protons in our body. These protons are essentially free hydrogen atoms, meaning hydrogen nuclei without electrons. Since our bodies are mostly water, about 60%, which contains 2 hydrogen atoms for every oxygen atom, there are plenty of protons around. Each of these protons acts like a tiny magnet, with a north and south pole, thanks to their positive charge. When we place the body in a magnetic field, these protons align with the field, and their behavior under the influence of radio frequency pulses allows us to generate detailed images. So, in essence, MRI leverages the magnetic properties of protons in water molecules to create the images we use in medical diagnostics. So, how do we actually get an image from these tiny oscillations of flipped hydrogen protons in the brain? Well, MRI uses the movement of these small magnets within a magnetic field to generate an image. Inside the MRI scanner, these protons align themselves parallel to the strong, constant magnetic field. Now, when a short burst of electrical current, what we call a pulse, is applied to the patient's tissue, it disturbs this parallel alignment. When the pulse stops, the protons return to their original position, releasing the energy they absorbed. Here's the interesting part. Different types of tissues, like gray matter, white matter, or blood, release different amounts of this energy. A special device detects this released energy as tiny electrical currents. These electrical signals are then converted into an image by a computer. Because each tissue type releases a unique amount of energy, the resulting image is highly detailed, allowing us to see the inside of the brain with great clarity. So, in essence, MRI works by measuring how these protons respond to magnetic fields and pulses, and by translating that response into the detailed images we rely on for diagnosis and research. Let's explore how X-ray imaging works. It's based on the absorption of X-rays as they pass through different parts of a patient's body. Essentially, tissues absorb X-rays to varying degrees depending on their density. This variation creates a shadow image, or what we call a shadowgram, allowing us to see inside the body. Now, the body is made up of many tissues containing different elements. These elements differ by their atomic number, which is the number of protons in the nucleus. The key point here is that the higher the atomic number, the denser the element, and the more effectively it blocks X-rays. For example, when X-rays hit calcium in cortical bone, they are strongly absorbed or blocked, so the bone appears white on the radiograph. On the other hand, elements like nitrogen, which are less dense, allow X-rays to pass through more easily. That's why the lungs, which contain air and are less dense, appear darker or almost black on the image. When there's a fracture in the bone, the fracture line appears dark because X-rays pass through the break more readily, while the surrounding intact bone remains white. This principle of differential absorption based on tissue density is fundamental to how X-ray images give us such detailed internal views. During a regular X-ray procedure, a stationary machine sends X-rays through the body to create a single shadow picture. It's a quick way to get a basic image of what's happening inside. But with a computed tomography, or CT scan, things get a bit more advanced. Instead of just one picture, computers and rotating X-ray machines work together to produce many successive images, called tomograms. These images are taken from different directions, giving us a more comprehensive view of the inside of the body. In a CT scan, the X-ray source and the detectors rotate simultaneously, but in opposite directions. This coordinated movement allows the system to gather detailed information from multiple angles. As the patient lies on a motorized table, it slowly moves through a circular opening in the CT scanner. While the patient passes through, the X-ray source rotates around inside the circular opening. On the other side, detectors record the X-rays that exit the body. This rotation captures numerous images of the section being irradiated. The result is a set of detailed images that provide much more information than regular X-rays. This makes CT scans especially useful for diagnosing complex conditions, as they give us a clearer picture of what's happening inside the body. Now, one of the most familiar clinical uses of sound is through the use of a stethoscope. This simple yet powerful instrument consists of a small bell-shaped cavity connected to a hollow, flexible tube. When a healthcare provider places the bell on the skin over an organ like the heart, lungs, or intestines, it acts as a receiver for the sounds generated within the body. The sound waves are then transmitted through the tube to the examiner's ears, allowing them to assess how well the organ is functioning. The stethoscope was actually developed back in 1816 by a French physician named René Laennec. Since then, it has become an essential tool in medical diagnosis. With a stethoscope, doctors can listen to sounds produced by the heart, lungs, or intestines, and even observe blood flow in arteries and veins. It's capable of detecting sound waves with frequencies ranging from tens to thousands of hertz, which covers a wide spectrum of physiological sounds. Overall, the stethoscope exemplifies how sound analysis plays a crucial role in clinical diagnosis, helping us non-invasively monitor and understand the body's internal workings. Today, we're diving into the fascinating world of ultrasound. Now, if the frequency of a sound wave exceeds 20 kHz, which is 0.02 MHz, we call it ultrasonic or ultrasound. These high-frequency waves are beyond our hearing range but have incredible applications, especially in medicine. Typically, medical ultrasound uses frequencies between 3.5 and 10 megahertz. These waves can penetrate tissues in the body, but as they do, they encounter different structures, leading to reflection, scattering, and absorption. This interaction is key because it allows us to gather information about the tissue's form and structure. Here's how it works. An ultrasound machine sends a wave into the body tissue. When that wave hits different tissues, part of it gets reflected back, scattering in various directions. The machine detects these reflected waves, which then generate tiny electric currents. These currents are amplified and processed to create the ultrasound images we see on the monitor. Now, when we look at these images, they are often described with three terms: anechoic, hypoechoic, and hyperechoic. These describe how tissues appear based on how much sound they reflect or absorb. Anechoic areas are typically fluid-filled, appearing dark. Hypoechoic areas are less dense, appearing darker than surrounding tissue, and hyperechoic areas are denser or more reflective, appearing brighter. So, in summary, ultrasound is a powerful, non-invasive tool that uses high-frequency sound waves to visualize internal body structures by analyzing how these waves are reflected and scattered. It's a perfect example of how physics principles are applied in medicine to improve diagnosis and patient care. Now let's look at some important terms related to ultrasound imaging. First, we have anechoic areas, which appear completely black on the image. This is because they don't send back any sound waves at all, making them echoless regions. These areas are usually filled with fluid, like cysts or blood, which explains why they don't reflect sound. Next, there are hypoechoic regions. These give off fewer echoes, so they look dark gray on the ultrasound. They don't send back a lot of sound waves, meaning they are less reflective than surrounding tissues. This can indicate tissues that are denser or less fluid-filled. Then we have hyperechoic areas, which bounce back many sound waves. These regions appear as light gray on the image because they are highly reflective. They often represent dense tissues like bone or calcifications. Connecting this to our overall theme, understanding these differences in echo patterns helps us interpret ultrasound images more accurately. Recognizing what appears black, dark gray, or light gray allows us to identify various tissue types and abnormalities effectively. Now, let's talk about the energies of X-rays, gamma rays, and radioactive particles. These particles have energies that are much higher than the energies that hold electrons in atoms and molecules together. This means that when such radiation enters biological tissues, it can actually rip electrons away from molecules, causing significant changes in their structure. This destructive potential is not just a hazard, it can be harnessed for good. In controlled doses, radiation can be used therapeutically, especially in cancer treatment. For example, a small amount of radioactive material like radium or cobalt-60 can be placed inside the body, near the tumor. By carefully positioning this radioactive source and precisely controlling the dose, doctors can target and destroy cancer cells while minimizing damage to the surrounding healthy tissue. This is a powerful example of how understanding radiation energies and their interactions with biological matter can be used to save lives. Today, I want to talk about another important method for treating cancer, using an externally applied beam of gamma rays or X-rays. This technique is quite effective because it allows us to target the tumor directly without the need for surgery. One of the biggest advantages is that this treatment is non-invasive, meaning the patient doesn't have to go through surgery, which can be quite invasive and recovery-intensive. Now, a key challenge with radiation therapy is protecting healthy tissue. To minimize damage, we can frequently change the direction of the beam as it passes through the body. By doing this, we ensure that the tumor remains in the path of the beam and receives a high dose of radiation, while the surrounding healthy tissue gets less exposure overall. This approach helps to maximize the destruction of the cancerous cells while reducing side effects and damage to healthy tissue. It's a great example of how precision in medical physics can significantly improve treatment outcomes. So, in essence, by carefully controlling the direction of the radiation beam, we can effectively target tumors and spare healthy tissue, making this a powerful tool in cancer treatment.